Well, that's just because we haven't prayed yet.
You know, I almost forget that every week. Sometimes I remember at the end, but Lord, we went under attack, and it's not much fun to deal with, but we know that you're in there and everything will work out. We just pray that we can figure out who this person is and lead them to the Lord, because they got some reason they don't want us here. It's sad. But anyway, Father, just be with us all, especially me as I'm trying to teach, and just fill everybody with your Holy Spirit and help them to learn tonight. We got a lot of stuff to cover. So anyway, let's all right, for review, we're going to talk about phase angle, which we're not going to demonstrate. Ann pointed out last week, well, that looks like it's right on top of the other one. Well, it's not supposed to be. I don't know. My gosh, reactance, capacitive reactance, and inductive reactance. Did you have a question? No. Okay, impedance and resonance.
I finally feel I'm on top of the last week's material.
Oh, cool. Wow, congratulations.
Yeah, it's the first time.
Phase angle capacitive. We know that when we apply a voltage, let's just say we apply a DC voltage to a capacitor, immediately the current goes from 0, which is right here, straight up, very, very fast. And as the voltage comes up, the current drops off. So as the voltage approaches its full amount, the current drops down till the current reaches almost 0 and the voltage almost reaches its full potential. But that means the current is happening before the voltage. So let's take a look at that. Phase angle, capacitive. Here's the voltage. As soon as there's 0 volts, here's an AC signal. And this point right here, as soon as the voltage starts, the current jumps up here to a high level. And as the voltage comes up, the current drops off until the voltage hits its peak and starts going down. And at that time, the current's passing through 0. So same thing going down. As the voltage drops, the current is dropping and headed toward the other direction. Now,
Oh, Joe?
Yes.
And at that point, the capacitor is charged, right?
At this point right here.
Yep.
At 90 degrees, it's charged. But the current is behind the voltage. So we say the current lags the voltage. And so that's the phase of it. It lags. It is behind the voltage. Now, when we go to inductance, here we've got a whole bunch of stuff going on, but here when the voltage starts, and remember we talked about an inductor. When the first coil gets a little bit of current, it creates a magnetic field that goes to the rest of the coils, which then in turn makes a back EMF, electromotive force, a backwards force that prevents the current from going. So at that point, I'm sorry, this is the voltage. I mean, this is the current right here. If the voltage starts out here, the current is here. So as the voltage goes down, then the induced voltage is going from being down toward the positive, and then that allows the current to get started. So notice that the voltage that's applied here is behind the current. So the current in this case leads the voltage because it's in front.
That's not what your note says.
Well, that's correct.
And that's correct.
The current lags the voltage.
Because the voltage comes first.
because the applied voltage comes first and then the current. Sure, you're keeping me on my toes.
Okay.
I know, that's good. That's good. Now, does everybody understand that?
Yep.
Yeah, okay, all right. I just want to make sure. Okay. Capacitive reactance. This is the formula for it. The thing that we want to note here is it's an inverse, right? Inverse, we got 1 over something. As the capacitance gets bigger, the reactance, which is X sub C here, gets smaller. As the frequency gets bigger, X sub C gets smaller. So the reactance gets smaller. Follow that?
Mm-hmm.
So, and then we go on to, well, this is an oscilloscope presentation. We're not going to do that again this week unless anybody want me to do it. No? Okay, good. Now, inductive reactance. And then, now what is reactance measured in?
Microfarad.
No, that's
Oh,
its
that's-
unit,
Ohms.
ohms. It's a resistance. Except it's the resistance of a reactor or either a capacitor or an inductor. So here, if the inductance goes up, the reactance goes up. If the frequency goes up, the reactance goes up. Capiche?
Capisco.
Ah, good. Okay, we've got that. And we're going to skip that. How did I end up with two
So
of
do
those?
we have to calculate those, or we just are looking at the relationships?
Right now, we're looking at the relationships. If you're taking the amateur extra class,
Mhm.
you will need to know those formulas and be able to use them.
Okay.
So, and in that, remember, if you do capacitance in microfarads and frequency in megahertz, that makes it a lot easier to work out. Because otherwise you're working with some really big numbers, which are hard to work with. You got a good calculator, it doesn't matter. Anyway. Okay, now what's coming up? Now remember, we talked a little bit about rectangular and polar coordinates last time. Somebody, let's see how, if anybody learned here. Does anybody want to tell me about rectangular and polar coordinates? No?
Well, you mean what
No.
are they? Why do we care?
Yes, well, that's good. Yes, why do we care?
Yeah, I'm always caught up on that one.
Okay, well,
We're plotting.
we're,
When you need a Smith chart, that's when you're going to need to care.
yes, well, actually, and other times also. All of our antenna analyzers give you the information in polar coordinates. When you measure something, it might say 40 ohms plus J 32. So you need to understand what that is. And the polar coordinates, or excuse me, the rectangular coordinates, both of them actually help us visualize that. And it the diagonal pointer in either the polar coordinates or the rectangular coordinates is the actual impedance that we're looking for.
Of an antenna, right? Aren't we
Pardon?
we're talking about properties of antennas.
Well, that is just one thing. Coax antennas, your transmitter, and lots of other stuff also.
Yep.
Okay, so anything that has an impedance.
Correct,
Okay,
correct.
So all, in my mind, all of this has been a way to understand how to achieve or how to know what your impedance level is. Probably grossly oversimplified.
No, that's really, well, the other principles that we've been talking about have other applications. So besides impedance, I mean, in circuits, you want to know what their reactance is because you're trying to do specific things. Tonight, we're going to cover reactive power and power factor. Mostly in practicality, we find those in power generators. Q factor, how good a capacitor is, how good an inductor is, how good a LC resonant circuit is, and magnetic cores. So let's move on, but still a little bit more trigonometry. We probably remember these from high school. Some of us may have somehow got out of taking these classes, but the sine is the opposite over the hypotenuse, as we can see here. Here's the sine, it's the opposite, whatever length that is, over the top of this. And the cosine is this adjacent one over the hypotenuse, which is this one right here. And tangent is the opposite, which is over here, over that one. And if you know theta, so if you know any two of these in a right triangle, you can find out all the rest. Knowing this helps you to understand what the math is about that's coming up. It's not absolutely necessary. You can memorize the formula and do it. But Scott, you're right, a Smith chart. And I looked hard for this one. And there's a reason I picked this one out, because a Smith chart is a very complex. They have literally 100 or, I don't know how many lines between here and here. And also these are just filled with many, many lines. And so it gets kind of confusing. But see this one right here in the middle? You can either call that 50 ohms or 75 ohms or 300 ohms. Mostly we call it, because we work in 50 ohm systems, 50 ohms right there. So 2 over here would be 100 ohms, and 0.5 over here would be 25 ohms. So, and this line here is the purely resistive line. Here is infinite resistance over here, and over here is a dead short. And notice that these say plus J. So we got plus J1, plus J.5. That is the inductive side. Now, do I have it right? I hope so. And minus J, this is the capacitive side. So if you had a point, oh shoot, I had to click on it. If you had a point right here, we'll call it right here. 0.5, that's 25 ohms, and then minus J.2. And you've seen that, you'll see here in a little bit, but this is just so that you start getting this into your mind, because later we will be studying it in more detail. You could possibly go the rest of your life and never use a Smith chart. But if you ever start using them for applications, especially in antennas and coaxial wire and that kind of stuff, they're very handy to use. Here's rectangular coordinates. And remember, we're talking about X. This is the X-axis. Here's plus X. Here's the Y-axis. And this will become the imaginary axis. So this is the J. So if you have a 3 by 2, this is 3 over 2 up, or it could be remember our sample we showed on the Smith chart, 25 ohms. We'll call that right there, plus 0.2 J, which would be up here somewhere. And this point right here would be the reference for it. So it just helps you visualize how it works. And you have minuses, you could do all the way around. But mostly in our applications, it's here. So here's polar coordinates. And here we're worried about the angle. And remember that I in mathematics is J in electronics. What is I in electronics?
Current.
Way back in the beginning.
What was that?
Yes, it's on this piece of paper right here.
Current.
What's I equals E over R? What is I?
Current.
Current, right. So we use J in electronics. But here's the imaginary line here. So you got X, Z is equal to X, which is the real resistance, plus the imaginary. And then the R here is Z, which is the impedance. So that's the impedance there. Okay, next one. Writing and graphing impedance and phase angle. I'm just going to read this. The impedance values are written in rectangular form as Z, which is impedance, equals R, now that's the real R, plus an imaginary number, plus JX, where the value of reactant X can be positive, which is inductive, like this right here. See, plus J, that's inductive, or negative, and here we got a minus J, which is capacitive. And then they have the example 50 ohms minus J, 25 ohms, which would be 2.5 on our scale. So, or 50 ohms of resistance, 25 ohms of capacitive reactance. And notice these here.
So I'm sorry, Joe, how is it that you can add or subtract resist? I mean, you're not really adding and subtracting, right? You're just notating what these two values are. I mean, they're not the same concept, so I don't see how we're combining or discombining them.
As I'm explaining them to you right now,
Yeah.
I'm showing you how to visualize the concept. There are methods for adding these. I don't know how to do them.
Okay, all right. So we're just, okay, I got it. We're plotting another.
Yeah,
Okay.
but with the Smith chart, you can actually do all the mathematics physically by using dividers.
Yeah,
That's why people use the Smith charts.
okay.
Does that not satisfy you?
I don't.
Well, this,
I have to work at it.
yeah,
Sorry, yeah.
no, these are good questions. The thing is we will be covering this later in the class.
Okay,
So you'll get to actually see it being done. But that's, I mean, we're going to be way down talking about antennas and stuff at that time, which is way, way down in the class. So here's impedance. Notice we've got rectangular coordinates, and that is from here to here and from here to here. So here's X plus IY, that's rectangular. And then we've got polar coordinates, which is the theta angle and R, which ends up giving us this figure right here, which can you can, with trigonometry, you can mathematically figure out what that is if you know what this is and you know what the phase angle is. Remember, we were talking about inductive and capacitive phase angles. They're real. So if it's anyway, moving on. I'm just going to repeat it here. Plus J is inductive. If you're looking at the Smith chart, it's the upper part of the chart. If it's negative, it's capacitive. You look at the bottom part of the chart. And remember that I equals J. And I'm not going to repeat this again. I think by now. Now, here again is the Smith chart. And I want you people to kind of get familiar with this little guy here. Right in the middle is 50 ohms. This is the real resistance line. So if you go with R plus J, that line is the R, and plus J is up here. And if you go with the negative J, you come back down here, it's down here. And through looking at this and doing measurements, you can take a point that's up over here and figure out what you need to do to get that point to go from here back down to here. When you have an antenna tuner,
Oh, Joe.
yes,
So just maybe as an example to folks, what folks don't really realize is this Smith chart thing there, that's actually a little calculator for you.
oh, correct.
Okay, so
Yeah,
they're
oh,
wondering,
thank you,
why
yeah.
would you ever want that Smith chart thing? Well, that's actually a calculator right there.
It is. It's a very, very powerful tool. But I want to show you, if you have one of these, here I got to figure out, this is an quote antenna tuner. I don't like that name. I call it a transmatch. But inside, look at the coil and the capacitors. Oops, I'm on the wrong side here. There's the coil, and then there's two capacitors.
Yeah, turn it over by kind of on a side view, would you?
Oops.
Yeah, there you go, so they can see the coil.
Yeah, there. Oops, it's kind of hard to do backwards, but there's. Oh, that's the capacitor, and oops, here's the coil. I'm not quite used to doing stuff backwards, but anyway, there you go.
Yep.
Okay. Now you can convert from rectangular to polar this way through these formulas, which we went over last week, or we can go from polar to rectangular just by doing this. You can, if you've got a calculator with a scientific calculator, and most phones have those, you can perform these functions pretty easy. If you just simply sit down and start playing with your calculator, pretty soon you'll figure out how to do it. That's how I figured it out. So anyway, resonance. Now, notice this formula. Resonance, now resonance happens when the reactive capacitance of the reactive capacitance is equal to the inductive capacitance. So when those two inductance are equal, that's resonance. And that's something that you need to remember. That's on the test, by the way. Most of the tests have that.
Yep.
Okay. Now this formula here, FR of resonance, is right here. And then we got 2 pi, and everybody knows what pi is, 3.1416. Nobody's going to finish that.
1414.
I don't remember what it is. And then there's inductance here, and then there's capacitance. So you take the inductance times capacitance, take the square root of it, multiply it by 2 pi, and divide all that into 1, and you come up with the frequency of resonance. So now there's 2 kinds of things that can be in resonate. The capacitor and the inductor can be in series like this. So when they're in resonance, you're going to have the minimum impedance. When they are in parallel like this, you're going to have the maximum impedance. And notice that there's an R here, there's an R here, and there's an R here. There's no such thing as a pure capacitor or a pure inductor. They have resistance built in. So in all these formulas, they throw in a little bit of resistance to help indicate that that's true. And you can also put real resistance in there to accomplish different things. So the reactive power and power factor. Now, folks, I hope some engineer sees this and he can get me straightened out on all the practical applications of this. Some of it falls back on our inductive and capacitance and reactance and resonance. It helps us to understand that. The only place I've seen these myself personally is on generators, AC generators, and they'll have I will explain it, volt amperes and volt amperes reactive. So now we all remember these and sitting back here laughing at me.
It's all great to me.
Oh, good. I'm glad I've got you snowed. Now these power formulas we've all studied before. And if it's a resistive load, these fit. We don't have to worry about anything about them at all. But let's talk about reactive power. Power in a reactive load is VA. That's voltage times amperes, which is simply right here. Voltage, which is E, times I, the current. So that's the apparent power. If you are running a huge resistive load, or just light bulbs, which are simply resistance, that works. But if you're running your vacuum cleaner or a motor, that is a reactive load. And the actual power dissipated will not be that. And I like thinking about motors. A motor is an inductive load. And if it's running free, it draws very little current.
What does that mean, running free?
Running free, that means it doesn't have a load. In other words, you just,
I mean, it's just running.
yeah, it's just running and there's no load on it. There's
It's
no
not doing it.
fan. It's not mowing the lawn. Yeah, it's not doing anything.
Like in idle.
It's not pumping water.
Good way to put it.
Now idling at 3,600 RPM or whatever you want to do. But as soon as you put a load on it, as soon as you start pumping water and making it work, it takes on a load. So when it does that, it's transferring the electrical energy going into it into a mechanical load. So that becomes a real power. So reactive power, it's non-productive. It's a wattless power. So if you start a motor, actually all the power that you're using is just spinning, just keeping the motor spinning. Very, very little power is being used until you put a load on it. Now, VAR, volt amperes reactive. Now I'm going to read this. Only the resistive part of the circuit consumes and dissipates power as heat. That's That's question number E5D09. One of those that you for sure need to know. There, folks, there in the book, there are many questions associated with this. I'm hoping to just give you an idea of how it works. And then if you're going for your test, you need to study the questions and understand what the answers are. And if you have any questions about that, be sure you'll give me a call so that we can discuss it and work it through. And down here, remember, power in a real resistor is pure power. But in a resistor, it's just dissipated as heat. In an inductor and a motor, the power is dissipated as a physical force as it moves something. When we see my T, see my T now, I just did work. I actually did something. And when I let it down, it's negative power. Actually, when I go across, when I go across this way, I don't do any work.
That knee,
Huh?
that knee.
Well, that's the technical thing. So anyway, let's move on. Reactive power is these are the formulas. There's the power factor is what we use to figure out if we have the apparent power, we can figure out what the real power is with that. So that is power, the real power being consumed over the apparent power. And the apparent power is just voltage times amps. So if you've got a motor and the power factor is 80%, if it's drawing we'll just say 100 watts, then the real power being used would be 80 watts. So let me make sure I said that right. The apparent power is 100 watts and the power factor is 80%, then the real power being used is 80 watts. Oh, and that's this formula down here. I'm getting ahead of myself. Any questions?
So once again, these power real we can calculate because we have those formulas that we learned in the beginning.
Correct.
But power apparent, where do we get that from?
Power apparent is simply the voltage. If you have a voltmeter and an ammeter and you measure it.
Okay, so again, it's a measure.
Yeah, if you're dealing with a motor, you'd probably measure 120 volt AC. Then you had an ammeter clamp on and it measured 10 amps. That is the apparent power.
Okay.
Next question, any more? Okay. When the power factor equals 0, there's no real power. Okay, when you got a motor running freely, it's the power factor. Well, I don't know if that's right. It's drawing almost zero power.
Anything times 0 is 0.
Correct. Practical circuits which contain resistance. The power factor will be somewhat less than 1, always. Because there are always, in every real circuit, there are real resistances and real losses.
So 1 being 100% or?
Correct.
Yeah, okay.
Yeah. one is 100%. The real power will always be something less than the apparent power.
Seems like it should be the other way around. I'm not.
Yeah, the
always gonna
apparent,
get
yeah,
that one.
but the thing is, it says apparent power. So that's not the real thing. And you go down from there.
Yeah, okay.
Okay. These facts that I just told you are very important to remember.
One of the places that you're going to be using them is when we talk about transmission lines, huh?
Scott, I'm not sure I understand what you're saying. Can you explain it to me? I guess not.
That,
You didn't hear what you said.
Did you hear what I said?
oh, well, I thought you were talking maybe about power factors of a power factor of a certain type of coax.
I don't know if that applies.
Okay.
There's a lot of, guys, there's a lot of stuff I don't know. So
Oh, that's good to hear, Joe.
yeah,
Most encouraging.
Yeah,
yeah.
I
Well,
don't have to know it.
there are places where I go where I feel really dumb. Let's be honest about this. So anyway, okay. Q. Oh, what time is it?
It's 15 minutes after 7.
Okay. Somebody want to let me know when it gets to
7:30.
7:30 for our break. John's not here. I really miss John. John is so helpful. He's got little pieces of paper he holds up to tell me to do things, and I just hope I'm not messing up. Q.
Okay, so then P, now we have Q.
Now, yeah, but the sad part about this, that there's something else called Q too, so we got to be real careful what we do. Make sure we properly apply our Q. The quality factor, it's basically how good is the inductor and the capacitor that we have, especially when you got a resonant circuit. If you're trying to run a lot of power through a little tiny wire, it's going to have a really, really low Q. And we will get into the details of this as we go on. It's to measure it, you take either the inductive or the capacitive reactance and you divide it by the real R. So if the real R is big, the Q is low. So if you take an inductor or capacitor and you put a 100K resistor in series with it, it's going to be a really low Q circuit. If you only have 0.02 ohms, the Q is going to be very big. So if you take an inductor, recognize this guy here. This is an inductor. I wound it so I'd have something to demonstrate to you people. This would have a fairly high Q as it is right now. It's a pretty heavy wire, and as long as we're not trying to run 1,000 watts through it, it would work pretty well. So, and the resistance of this will be in milliohms. This might be all of 2 or 3 milliohms, which is a very low resistance. And I have a, by the way, if anybody has something that they want to measure the extreme low resistance of, I have a meter that will measure this.
Hmm.
I mean, I can measure down to a fraction of a milliohm. So now there's something else also. If you're trying to build a transmitter, and if you have a low Q and it's not working on, let's say, the output of a linear amplifier, you cannot do anything to the components that are in there to make it have a higher Q. You have to do something to improve those components.
Mhm.
And I'm gonna maybe
So, but Joe, your chart here says that Q is a measure of a component. Right? So we don't really build components, do we? Isn't that our starting point?
what do you?
I mean,
I'm not sure I quite understand your.
so a component is something that we put components together to make other things. So the component is the lowest level building block. I'm not sure. That's a question.
You see this? I built that component.
Yeah, but it's unitary. It's not made up of more than one thing.
Oh, yes. Yes, this is just one component.
So here's my question. So in order to get a better Q, oh, well, so I'm confused because the Q would seem to be a constant based on
This component
thing.
here,
it's going to have a constant Q.
correct. And there's nothing I can do to this to improve it.
Yeah, okay.
In order to improve this, I'd have to get much bigger wire and make a much physically larger coil.
Okay, I see.
And we're going to get into some concepts in tonight that talk about how to improve the ability of a component to work. Now, capacitors and let's actually get out of this here.
We got the pad.
Yes, indeed.
Ah, good. Okay, now I can show you stuff. Oh, capacitors. This capacitor in itself and by its design is pretty much a very high Q part. And you can't change that much.
So do you know that by looking at it or just because you know that particular capacitor?
I know that because the book that I just read said the capacitors are that way.
Okay.
That's how I know.
Good enough.
It works.
Now I want to get this.
The interesting thing.
Remember this from earlier in the year? Am I going the wrong? Oh, I know it's, okay, here we go. Well, here are a series of coils, and then there's this one here, which I'm going to turn over this way. Notice how big this is compared to this. This is because this is getting into a very high frequency. And as frequency goes up, there is, oh shoot. There's the skin effect. If you have DC, the whole thickness of the wire runs current. So it doesn't matter whether it's this size or this size. If it's a low current, it makes no difference at all. But when you apply AC and you start going up in frequency, the current flows closer. Here's the end of a wire. When you have DC, the whole wire has current flowing through it. When you get up to 100 megahertz, only the outer skin of the wire is carrying electricity.
Why
So-
is that? What causes that?
I don't really understand it.
Okay.
That's something I do not know. I do know that it's real, and I've seen its effect.
So the center of that wire is,
Yeah, the center wire's not doing anything. You
No.
might as well be a pipe.
okay,
60 cycle AC does not have much skin effect. 3 megahertz has quite a bit. 100 megahertz has a lot more. This part of this coil here is supposed to work at 30 megahertz.
So does that affect the heat that's being produced as well?
Yes. Yeah, because the resistance, if you were just using these little tiny wires here,
Mhm.
and the skin effect would cause the current to go through just the outside of that. Notice that the skin of this wire is much smaller than the skin of this wire.
Mhm.
So this has a lot lower resistance.
Yep.
I'm pausing to let this sink in. And this is an important concept to understand.
One more minute.
Oh, okay. Well, I'll tell you what. Let's go back to here, and we'll take our break. Okay, back to Q. Had we covered?
Yep.
Oh, yes, there's no way to raise the Q of a component without building it with less parasitic resistance. Q in a resonance circuit is pretty much a part of what the inductor is. If you got a little tiny inductor, it will have a pretty low Q. So, and that depends on the frequency. If you're working at 3.5 megahertz, if you're working at 144 megahertz, you better have the right components in there. And when you get to like with this, that's for this portion is for 30 megahertz or 28 megahertz, excuse me, 10 meters.
So what is that thing actually?
This is, you recognize it as a coil, right?
Yeah.
You put a coil and a capacitor together, and it becomes a resonant circuit. This is this is part of the pi network of a 2000 watt transmitter. And we will later be studying what pi circuits are and how they work. Now, unfortunately, a pi circuit I cannot mathematically show you, but I can show you how it functions. It'll take the output impedance of a tube, which might be 2000 ohms, and turn it into 50 ohms.
Jeez.
So that's what this
So does it produce a
with
lot of heat?
this.
I mean,
No, these parts don't Capacitors and inductors don't produce
Yes,
any
heat.
heat.
Oh, well, you're taking a lot of energy though, right?
Right,
By reducing-
remember
if you're
what,
compressing it down, I'm assuming that's my visual image. Or filtering it out, maybe it's the other way.
uh,
Or-
a pure resistance and a pure capacitance, neither one of them use any power at all. Therefore, no real power, so they don't generate any heat.
Mhm.
But if you're dealing with this and you're running a full 1500 watts CW,
Yeah,
and you turn off the power, you disconnect the 2025, no, I think it's 2800 volts that was on this. And you touch this, it's going to be hot. Because that does create enough current for it to get warm. But it's not, you're not going to, it's not going to be like a heater
yeah.
where you're trying to generate heat. It's just because there is a little bit of resistance in this portion right here. It's in milliohms. But because of skin effect, the resistance of this becomes higher at 30 megahertz.
Mhm.
Folks, I hope I can present this to you. I'm not sure of my full understanding of it. If we are at non-residence, we use of an inductor capacitor in series or parallel. We use these formulas to figure out what the Q is. If they are in resonance, then we use these formulas here. But start out with, if you got an RLC network, that's resistance, inductance, capacitance. Q depends on if it is in series or parallel. If it is in series, increasing R or increasing losses will lower the Q. And you know, I just thought of something. What might help you out is if I move ahead just a little bit to show you this is my here, I'm gonna pull this off here a little bit. This is the effects of Q here. Here's a Q of 10. See this dotted line? And this is the output of a resonant circuit. Remember when I had a resistor and capacitor in parallel, and as I went from low frequency to high frequency, it went up and then it came down again. Okay, here is a fairly low Q, and notice how wide it is here at the -3 dB point. Here's a Q of 100. See how sharp that is?
Mhm.
So if you have a high Q, your resonance has a much narrower bandpass. It's only going from here to here. See, this is frequency. Here is your resonant frequency. 1 is resonant frequency. It might be 14.1 megahertz, for instance. But here's the bandwidth from here to here. But with a Q of 10, the bandwidth goes from here to here. So the low Q has a broad tuning, and a high Q has a very narrow tuning. And now there are circuits that you want to have a broad bandwidth. So you would want to actually create a low Q. So let's back up. to these here. Now we're talking about Q again. These are just formulas. Look, if you learn what these are and why we have them, you can go to your book, look up the formula, read it, remember, and put it to use. If you read it in your license manual, and then if you read it in your ARRL handbook, and then you look at it, you may not understand it immediately. If you have to ever put it to use, you'll know where to go, you'll know where to read about it, and then you'll apply it, and then you'll get real understanding. Are you understanding what I'm trying to show you here of the importance of this stuff?
Mhm.
I've never actually really measured or used Q directly. I have done it indirectly just by understanding how it works. I look at something and I say, "Oh, this has got a real low Q. It's going to be real broad, but this should have a real high Q." It's like my my transmitter coils that I just showed you. I understand why that you have the big, huge wire for 10 meters, because you need to have a lower Q. I mean, a higher Q, excuse me. Okay. So in series, if you have series resistance, R increases the losses. So you have a lower Q. If you have an increasing R when the capacitor and the inductor are in parallel, lower losses, and it raises the Q. Everybody, hands roll.
Well, I'm just trying to
Versus-
figure out what series and parallel. I mean, obviously,
an
It
inductor and a capacitor.
yeah.
Remember, we were talking about resonant circuits? We had series resonant circuits and we had parallel resonant circuits. A parallel resonant circuit will create this kind of chart. The impedance will go up and it'll cause the output to go up. Whereas if you have them in series, this would be either current or it would be going down like this.
So what I'm trying to, so if we understand how series and parallel circuits work, has anything to do with circuits, or is it just
Yes.
another one? It does, right?
Yeah.
So
yeah.
we should have been able to predict the relationship.
Yes.
Okay.
But you haven't got there yet.
You know
Well-
what? Yeah, I always get tripped up because we have 3 names for everything. That's why.
Yes,
Well, it's called jargon.
Yeah, I know, I'm well aware of that.
When you go to the doctor's office, they use jargon. And they're blah, 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 blah. And you have no idea what they're talking about. Except that good doctors and good nurses understand how to get around jargon. They don't use their jargon on you, and they're good to work with because they use vocabulary that you understand. But when they went through school, they used stuff that would just totally go over your head. And that's part of what we're trying to do here, is get you to understand the jargon.
Mhm.
This is a lot of this is learning the vocabulary. So now if you have a resonant circuit where you've got a capacitor and an inductor together, either in series or parallel, then you can use these 2 formulas down here to figure out what the Q is. So, and I'm going to read this. If in parallel, I should have put a dash in
Yeah.
here. Increasing R is equal to lower losses and raised Q. At resonance, just use reactance of either capacitor or inductance because
They're the
they
same.
are the same.
Well, that
You're
was
learning.
we started with that. That's about the only thing that made sense.
Yeah, well,
You're
I'm
gonna
proud of you. That's good. You know, one of the things we're recording this. And did I start the recording? I sure hope I did.
I don't know.
Huh? What, Scott?
I say, I don't know if you did or not.
I think I did. I think I pulled the thing up and restarted it. So
Okay.
anyway, so that you can go back to this and listen to it over and over and over again if you want to. This is this is a slide I should have had writing over here. Here is an inductor and a capacitor in series with R sub L. And here is a inductor and a capacitor in parallel with a resistance in parallel. And I'm going to read this. A series resonant circuit with a loss resistance of 100 ohms is shown at A, that's A right here, and a parallel resonant circuit with a loss resistance of 100,000 ohms here is shown in B. Q of the series circuit is 1,000 divided by 100, which equals 10. So that's this one here. So the Q of this is 10. Here's a parallel circuit with a 100,000 ohms in parallel. So you end up with 100,000 ohm divided by 5,000 ohms, which gives you a Q of 20. So this one has a higher Q. I actually remembered that. Now we have studied this in detail. Anybody want to discuss this? This is, by the way, this is how you actually find the delta D. Delta means the difference, right?
Mhm.
So the difference in frequencies is F of resonance, the frequency of resonance, which is right here, divided by Q. So if the Q is 100, that is the distance between here and here is much narrower. If the Q is 10, the distance from here to here is wider. So remember we talked about minus 3 dB. Oh boy, DF. Oh, I was going to put a delta in. I was going to find one of these and put it here. I didn't get time to do that today. I forgot. So the delta of F is equal to the half power bandwidth. So if you start up here and this is 100%, and you go down 3 dB, which is half the power from here down to here, minus 3 dB. Remember that?
Mhm.
That is so slick. How it came out that way, I don't know. Anyway, that's when you're talking about resonance, you're usually talking about minus 3 dB. So, any questions about this formula and its application? Nope.
No, not now.
Okay. Components at RF and microwave frequencies. Remember I talked about skin effect. That is a question. By the way, there are a lot more questions up here, but this is one I know that you should know and understand. If you do DC, as I talked about, it uses the whole wire. As the frequency goes up at 3 megahertz, there's a little bit of skin effect, but if you're at 100 megahertz, it's major skin effect. And all the current is running on the outside of the wire. You might as well just use tubing. And a lot of people do. They use tubing for those things. And you will notice in a lot of these transmitters that use coils, the coils are silver plated. Silver is a better conductor than copper. And so if you have silver on the outside, most of the current is running in that silver that's just plated on the outside. Nothing else is
Matters. So
yeah,
Well, you need the inner portion of that wire for structure.
correct.
But
That's all.
Other than that,
Yeah. Yeah. Okay. However, when skin effects up to a certain frequency, Q is improved with higher frequencies. After the skin effect takes over, then the Q decreases because of the increased resistance of the wire. I see shaking heads. Thank you, guys.
Mhm.
Here's a scale. This is at low frequencies, Q of an inductor is proportional to frequency. At high frequencies, increased losses in the inductor cause Qs to degrade from the expected value. So this, if it wasn't for skin effect, it would just keep rising like this. Q. But because of skin effect, this is what actually happens. Q, as you go up in frequency, Q starts dropping off. Now, self-resonance. This is something that will get you.
Yeah, among other things.
Well, you know, some of us will never try to build anything or do anything. You'll just purchase it, do it, buy it used, whatever. It's already built, it's already functioning, and it's working. There are some of us, like me, who likes to experiment and build things. Someday I will bring, well, it's awful heavy, but I will bring in my 1500 watt, 470 megahertz amplifier that I built for Dave Sanford.
has he ever gotten that back yet?
No, it's still sitting in my shop. He hasn't had any use for it. He wants to do moon bounce and he hasn't got the antennas set up to do it. I mean, he's going to have at least 4 antennas dividing the power of 1500 watts. I mean, it's you. And that's, by the way, when you're doing moon mounts, you either do CW or you do digital, and that's 100% duty cycle. So it's a lot of power.
It's a long way.
But I built that. I took an already design and I modified the design to do what we wanted to do. And I had to figure out some of these concepts to make sure that we didn't get ourselves in trouble. But notice this inductor here. If you have a coil, which is what we've got here, there's capacitance between this coil, this turn, and this turn. And then there's capacitance from here to here, and capacitance from here to here, and from here to here. They all add up. So if you've got a coil and it's close wound, you got quite a bit of capacitance. But you can see that as being in parallel with the inductor. So the inductor by itself, without anything on it, will have a point of resonance. That's called self-resonance.
And does it matter where that point is?
Oh yeah, it does matter. You don't want to have self-resonance, which is, see, if you look at this scale here, down in this area here, that inductor will work just fine. With any capacitor, you don't have to worry about anything. But if you approach its self-resonance, this is what happens. It goes through this and it's self-thread and makes all kinds of trouble. So
So is that to say resonance is a bad thing? We don't want it?
in this particular kind of circuit, yes. But you don't, when you design something, you design it so that the inside capacitance, you know, it's like, okay. Notice this coil here. Notice, here, I need to get this out of here. Notice how close these coils are. The capacitance between each one of these is not sufficient to affect when you're working at 3.5 megahertz. When you're at 3.5 megahertz, you're actually using all of, oops. You're using all of this. So you start from here and you go to here. So all of that is one inductor. But when you get to 30 megahertz or 28 megahertz, I should say, notice the spacing. That creates a lot less capacitance between here and here, and here and here, and then here and here, and from here to here. So you don't end up being anywhere near self-resonance, which is, that is what you do not want to have.
What would be the results if he did go into self-resonance?
It would
Charge?
also, it would oscillate probably, most likely, or it would just not, it would not tune.
Okay, thank you.
One of the two things. Because you would be tuning up where you would expect it to, but it would go into self-resonant, and then it would not work at the frequency you wanted it to be working at.
So if you found that situation and you shut down, pull the cover off, would you see a charred area or?
Probably not. No, not likely, although there are, honestly, there are situations where you can have things go really wrong.
Yeah.
If you're using tube amplifiers in linear amplifiers, we use like a 3-500 or two 3-500s. That's a 3-element, and we ground the grid, which reduces the capacitance from the cathode to the plate. You guys need to be able to see me talking here. Here's the cathode and here's the plate, and then there's a grid in the middle. If this grid is grounded, it eliminates what little capacitance it is between here and here. So a grounded grid does not have to be neutralized. But if you put in a tetrode, which has 4 elements, you've got your cathode, which is where the filament is that heats up to emits the electrons. Then you've got a grid, and then you've got a suppressor grid, and then you've got a plate. Well, there's the suppressor grid and the plate are close together, which creates quite a bit of capacitance. And the tube can go into self-oscillation because of that. And so they have excuse me. I'm trying to remember what they do to it. Neutralize. They have a neutralizing circuit that creates a capacitance feedback loop that's out of phase that neutralizes that capacitance. So the tube won't go into self-oscillation. Now, I want to tell you, I know that's true because when I was novice, I used a 6146 tube, which by the way was a fairly expensive tube. It was, I think it's a tetrode. It might be a pentode, but it had at least 4 elements in it. And it was my CW. It was going to be my 75-watt CW transmitter. And I built this thing from scratch, and it was gorgeous. I did this absolutely wonderful job, but I did not know how to neutralize it. And I fired that thing up. The first time I keyed it, it went flash. It lit up the whole room. Sparks were flying. Oh man, I couldn't unplug it fast enough. And I got brave enough, plugged it in again, and it never did it again. I don't know what happened.
It neutralized itself.
It neutralized itself. It worked.
And it worked after that.
Oh yeah, it worked fine after that. I think God was just helping me out, you know, even though I didn't believe in him then. But anyway, yeah, that was quite a thing. That happened in 1966, I think. Oh, that was a long time ago, and that was quite an experience. But I've since then learned how to neutralize them, and I have the equipment to neutralize, because you can measure the input, the output, and you can tweak it until there's no coupling. Anyway, but now back to keynote, share. Okay. So self-resonance. Do we need to know anything else about self-resonance? The distributed capacitance caused the combination of inductance and capacitance to resonate. This also happens with capacitor leads, which add inductance. So a capacitor can have self-resonance also. When you get it, especially at a really high frequency, you know, it's just a little length of wire. I mean, if you got a wire and it's this long, it has inductance. It's very, very small. It's in microhenries. I mean, it might even be less than 1 microhenry, but it has inductance. But when you're talking about 2.4 gigahertz, which is an extremely high frequency, that's a lot of inductance.
Mhm.
You know, so, you know, component, we'll be talking here in a little bit about why components are surface mounted. When they're surface mounted, you got extremely short leads and you get rid of all those problems. So it's a lot easier to work at really high frequencies. So, oh, that's what happens down here. The addition of surface mount components greatly shorten the leads, solving many problems. Now, if you, there's a lot of material that's in the book. I'd recommend that you read it, just read it through once. Unless you're planning on taking the extra exam. If you're planning on doing the extra exam, study it and study the questions and get them into your head. But for those of you that are going for technician or for general out there, don't concern yourself about it right now. But those are concepts to learn later. Now, magnetic cores. This is a subject that you should get to know fairly well. Now, let's take a look There are all kinds of cores. Let's just start looking here. Here's a coil that looks like the one that's in my my amplifier example here that I keep showing you. This is a power transformer, and here's the core of that. Here is a little coil. There's a little slug that's right in the middle of this, and if you have a tool that you put right down the middle of it, so usually they're six-sided little tool, and there's a core in there, and you just turn it, and it's threaded, and you can screw it in and out. So that changes the inductance of this coil. And these are actually the best coils to use for many applications. They're toroidal, and the thing about these is they keep the magnetic field into the center of the coil, and they don't go outside of it. Where if you got something like this, it radiates like this, bigger and bigger and bigger. These little guys here, it stays inside the center of the core. So there's air core, iron core, powdered iron, ferrite core. There's several different kinds of cores. This is an air core. This is a steel iron core. This has got a ferrite core. These are ferrite cores, these here. And each one of these, the permeability increases with each one. This has a very low permeability. So this is going to be a very low inductance. The henries of this will be low. Putting this steel one adds a lot, and it works pretty well especially at low frequencies like 60 hertz or 50 hertz, your house power. But these are steel ribs, and I'll explain why they do this kind of thing here in a little bit. This is a ferrite core, and it has the highest permeability. So if you've got X number of turns on here, it'll create more inductance than if you got a steel core or an air core. And that's the reason that they use ferrite cores. So, and that's a ferrite core, that is. And so you get a lot of inductance out of this. Less from this, even less from this. And this is the minimum amount of permeability that you have. I'm trying to get you to understand the concept. Now, with each one of these things, there are mathematical formulas. You can take a look at this. You can measure this, measure the diameter, figure out what the spacing is, number of turns, and you can actually calculate what the inductance of this is. I would just as soon grab remember this? That's an inductance tester. I grab it, slap it on there, and I know what it is. But if you're trying to create one of these coils with a given inductance, you need to learn how to use the formulas to figure that out. And for people who like to build stuff and create things on their own, that's an easy thing to do. Now, one of the problems with cores is that they can become saturated. In other words, they will, let's take the core of this power transformer here. It'll take only so much magnetic field. after you saturate it, you hit its maximum amount of magnetic field that it will handle, it will not work anymore. The output, if you put a pure sine wave, here's the primary of this transformer. If you put a pure sine wave in here, you will not get a pure sine wave out of it. And that's not nearly as important in a transformer like this. But when you get to these cores here, that is important. If you've got a little tiny toroid like this, and you try to run 1500 watts through it, you will saturate it and you'll distort your signal. So, and those are things that usually if you find a core, they will tell you how much power you can run through, what it'll take to saturate it. And so that's just something when you purchase a core, you're not, these things here, you're not going to manufacture them yourself.
Now, wouldn't you buy a core that had latitude above and below what you would like it to be? Or you buy a core just to that size?
I'm not sure I understand your question.
Well, what I'm saying is, if you were, say, going out to buy a core,
Yes,
now, you know what you need
correct.
in the circuit. Would you not buy a core bigger than what you would need? Or would you buy a core just to that size?
Oh, okay, now I understand your question. You're talking about for avoiding saturation.
Yeah.
You can buy it a satisfactory size or bigger.
Okay.
So you can use a larger core.
Yeah.
And then there will be less chance. It won't make any difference.
True.
And it'll cost you more money.
Okay.
You would not want to select a smaller core because it would become saturated.
Before you got to where you wanted to be.
Correct.
Yeah.
Thank you. Answer your question.
Well,
Now, with this core, notice there are a whole bunch of plates here. Excuse me. See these here, this is an E with a bar across this way, and then this is an E with a bar across the bottom. These are staggered as they go through here. And the reason they do that is it does prevent saturation, and it keeps no, I was just going to say something that's not true. So if you ever tear into one of these, you have to delaminate it to get it apart. One layer at a time. It's not an easy thing to do. But Scott, you've done that though, have you not?
Oh, you bet. You bet.
Yeah, you can take a transformer like this. You can tear it apart, pull this part out here, keep the primary, and then change the secondary. And you can change the voltages and do all kinds of things. You just completely rewind it and then put it all back together. And that was a popular thing to do in the 50s and 60s in amateur radio.
It sure was, because you couldn't afford to buy a real big, nice power transformer for your for a high power rig that you were building. So what you did was you would take and go into some place that had bad old TVs, and
I knew you were going to do that.
get the transformers from all those old TVs, and then you'd delaminate them and then stack those babies together and make a much bigger transformer.
Oh, what you just said, I never did.
Oh,
I never stacked them together. You're going to have to show me how you did that sometime.
okay.
Yeah. Oh, wonderful. The shape of the core is important. Now, here is a core, and it's an air core, but it's just wide open. And as I said, with this one, the inductive, the magnetic field goes like this, and it goes out, and it just keeps going out. With this, it keeps it pretty well contained within this, but some of the magnetic field does get outside of it. And you can actually, if you have a power transformer, you can actually induce some from this. But with this core, it's not too bad. But, and the same thing with this. With this core here, the field radiates outward. So if you had this here and then you had another one right next to it, they could interfere with each other. So if you're building something, you would have to put a shield in here to keep this one from affecting this one because of the magnetic field that goes out from it. But if you grab one of these, the magnetic field stays in the center. And then you don't have to, you could have these pretty close together and they won't affect each other.
What would you use for a shield?
Usually they just use, most of the radios I see, they use, no, steel.
Steel.
Yeah, chrome plated steel. But you can use also what's called, you could use mu metal. I don't know if anybody does. Mu metal is for magnetic fields. That's just something that popped into my head. I don't know. Let's see. It's 8:30. Now, this is something I probably should have done a larger picture of this. If you have a toroid and you run a wire through it, this first wire that you run through is considered to be one turn. So if you take that and then you put another turn around here, what you're looking at is actually two turns because you got this wire and you got that wire going through. Every time you pass a wire through the middle, it's an additional turn. Go ahead, Scott.
Oh, that's just interesting. I didn't realize that.
Oh, okay. Yeah, that's something I learned a long time ago. I have no idea where, but I was working on something, and these things here, you may very well work with if you like building stuff. Building your own ballon, which is a ballon, balanced to unbalanced. In other words, if you have a dipole antenna, which is a balanced surface, that area that you're working in, and then you go to coax, which is unbalanced, the ballon helps make it match properly. And with that, you end up with less current, less RF going down the outside of the coaxial wire. You can also use toroids. You just take these things here and you get 6 or 7 of them and you slide them over the top of the coax as it hooks up to the antenna, and it keeps RF from going back down the antenna. Now, speaking about permeability, these come in all kinds of material, and they have different kinds. Scott, do you remember some of it seems to me like there's a number 31 and a number 62 core material. Do you remember what those are?
No, because I didn't use too many toroids. I built toroids when I worked for Genie Industries. We would manufacture and sell toroids, mostly for the computer industry.
Yeah, and you'd use different mixtures, right?
Yep.
Yeah, yeah. And so just be aware that there's different mixtures that work at different frequencies. There are core materials that work really well at VHF, UHF, but they will not work with beams at 3.5 megahertz. So there are core materials that work well at that, and that's the kind of core material that you want to get. So just to be aware, when you're looking for a core, you want to get the right kind. If you find a core at some surplus place and it's really cheap, and they don't tell you what core material it is, you might buy one. And I've been trying to figure out how to test them to figure out how to do that. So there should be able to use a sweep oscillator and figure it out. But anyway, but that's a whole nother set.
More stuff, more stuff.
Yeah. Anyway, that's just something I've thought about. Now, do we have any questions on these cores?
The cores to the bottom on the left. And what would be the outcome of that if, say, you wrapped it-
These here,
Yeah.
or these here?
those?
Oh, these,
If
okay.
you wrap the, say, wrap 10 rings, 10 wires around through it,
Then it would, well, it would not, there is a formula that would tell you how much you have added to the inductance. I cannot tell you what that is right now.
so there's cases where you'd want less inductance or more inductance, and
Correct.
that would dictate the revolution.
Yeah,
Okay.
and you can use one of these for a transformer. You can put, in fact, your most of your radios use these for the output, and the primary is probably just about this, 2 turns, and then the output has several turns like this. So it goes from a very low impedance to 50 ohms impedance. And they're not shaped like this either. And I wish I had one of those. Let me go to the next stage. And I want to bring this transceiver over. Now this is real practical application. Here we have a whole bunch of bandpass filters. Notice the different sizes of the coil. We start with this little one down here, and then we go up to this one here, which has a whole bunch of turns on the coil. This one here, oops, excuse me, this one here. I need to look at what I'm doing, not at the camera. This one here, this is 28 megahertz. This one here is 3.5 megahertz. And in the schematic, they're all lined up in order from 3.5 megahertz to 28 megahertz. But you can see here we go from 28, 21. This one I think is 20 meters, 40 meters, and 80 meters. And the reason I know is because this has more coil and this will have more inductance. But these ones, you can see the capacitors down. Oh, you can see the capacitors down here and the coils. And this is a bandpass filter. And this one, I think I said was 20 meters. So it allows 20 meters to go through and not any of the rest. So this is a very practical application. Every one of your modern transceivers will have this between the amplifier that puts out your 100 watts and the antenna. And so here's the input side down here. And then this is the output side that goes to the antenna. This is a PL259 here on the end. So these are real practical applications if you're going to do this. This is,
Oh, Joe?
yes.
Yeah, sometime at some point here, can you show us where you get the 50
Power?
impedance of 50 ohms?
Each one of these filters, let's just take this one right here. By the way, this is a mechanical relay and this is a mechanical relay. So that when you want to use this band, these relays kick in and run the signal that comes from here through here. And so this is actually a specific kind of filter. And with these capacitors and this will be 50 ohms going through here. This is a coaxial cable here and it's 50 ohms. And as it goes through here, it always sees 50 ohms. And when it goes through the output, this is 50 ohms and goes over here and through here and comes out, which this here is 50 ohms impedance. Scott, I'm not sure I answered your question, though.
Yep, you did. You did.
Oh, okay, good. You know, I'm not sure. Yeah, no. I was hoping I had an amplifier that I could show you, but I don't have one. You guys, I will disassemble something. By the way, this radio here is dead. Not totally dead. I mean, it comes on, powers up, but it has what it has been nicknamed the creeping crud. And if you go on, you know, if you go online and you look up, and in this case, this is a Kenwood TS 440. And you look it up and you say problems, what comes up is creeping crud. And that's a very common problem with this. It's very hard to fix.
Explain yourself, what is creeping crud?
The front panel buttons, none of them really work.
Okay, thank you.
And it's just something in the manufacturing process was something that failed fairly early in the life of radio. So it's a common problem with this specific radio. So I don't know. Here's just while we're talking about it. This section right here with there's a motor here and a screw that turns capacitors that are inside of here. This is the automatic antenna tuner for this radio. I believe that all of this section here, it looks to me like it's got the IF and audio, and so this would probably be the main board. Going to see.
Don't buy that radio.
Yeah, exactly.
Well, you know, when it was new and operating, it was actually quite a good radio, but it ended its life.
What year did those come out anyway, roughly?
I don't know.
Yeah.
I don't-
70s, 80s, 70s?
I don't know.
Mhm.
If,
Don't know that one.
yeah, I might be able to, and in fact, I did, I pulled up the manual on it.
Yeah,
Uh, do you want me to try to figure that out, Scott?
nope,
Okay.
that's okay.
Yeah, I could go back and look. I think the manuals are still up on my computer. So, but anyway, here's. I'm,
It takes a lot of components to do.
yeah,
both
this
those
is,
things. That's-
Yeah.
now, talking about Scott, this is probably, I would guess somewhere in the 80s.
Uh-huh.
This is all discrete components. We have capacitors. All these are capacitors. These little guys right here are trimmer capacitors. We have, here's a filter right here. And by the way, we will start getting into components in chapter 5. And I'm kind of torn as to whether I should have you read the first part of chapter 5. And the reason that is that the first part of chapter 5 starts talking about how transistors and diodes and what they're made of and how it works. Now, that's kind of like why I didn't want you to read about polar coordinates and rectangular coordinates. Because if you have no idea why you're trying to learn this, it is senseless to you. If you have a little bit of an idea what it's going into, it'll make a lot more sense. So if you read chapter 5, and we'll be getting into chapter 5 next time, I probably will not talk about the first section. You want to show that to me, Bruce? Is that?
Oh, I'm just. And this is just scanning through.
Oh, okay. Well, don't worry about it. He hasn't quite got there yet. But anyway, here are some integrated circuits. Here and here and here. These are transistors. These little guys right here. And there's lots of connectors, which in wiring, of course. There are, let's see, here's a little integrated circuit it's a board with an IC on it, but it's vertically mounted on the radio. And I'm trying to, here's an inductor right here on the edge of the screen. This little guy right here. This here's a fan that keeps the transmitter section here cool. And the transmitter's inside this, but I haven't got that torn apart yet. So what I'm hoping is that you get some idea of what all these parts are, so that we can start making sense of how it all goes together. I'm trying to look and see if there's any. Well, I was thinking of some resistors.
Look very modern. doesn't it?
No, this is not very modern. Down here, there's a resistor. This little tiny guy right here. Here's one that's stuck on the end. I don't know if you can even see it, but it's got instead of being, and yeah, a lot of them are mounted on end. They just fold it over. But this is discrete components. Your modern rigs will not have components like this. They will be what's called surface mount. And they're little tiny things. And earlier, when I showed you stuff, I showed you surface mounted resistors. And some of them look like
Specs.
specs. Yeah, that's a good word. Thank you, Scott. That's all they look like, are specs. So let's see. While we're doing this,
What time to call it a day, isn't it?
we've got about a half an hour, although it's getting close.
No,
It's 8 o'clock, isn't it?
no, it's 8:45. 10 minutes to 9.
It's 8:52.
Oh, it's way past time.
Yeah,
Oh, I'm sorry, guys.
I know he's having so much fun here.
indeed he was. And it's all around.
This is the stuff I like to do. Oh, I am terribly sorry.
No, you're not, you're just caught.
That's okay.
Oh no, I do not want to do this. I'm sorry. I did not realize it was. See, John's not here. John always been. He would say, well, he'd hold his hand up like there's 5 minutes, and so I'd know to wrap it up. Well, I think the Lord blessed us tonight. Here, just before we go.
For next time.
Okay. Now, chapter 5. We're going to get into semiconductor devices. Materials, diodes, junction shock, A barrier, Zener, vacuum, light emitting, transistors, bipolar, field impact,
And how many
RF integrated devices.
Thank you, driver.
Okay, you guys tell me, would you rather that I start out by talking about these kind of components so that you can learn what the components are and how they function? This is when you do.
Is this a different chapter?
No. Remember, when I started this out, I said we're going to cover the materials for technician, general, and extra. The stuff in the book is mainly for extra class.
Yeah.
At the level it is at. But I would like you to understand how these other components function first, which is what I prefer to do, and then bring you up to chapter 5 in the book.
Whatever you think is best, Joe.
Go for it.
Okay, well, I'm going to do that. So anyway, I see that oh shoot, what's her name? Gave up on us. All right, well, good night, folks. Lord,
Thanks.
thank you. You guys.
Thanks, Joe.
Yes. Have a good one, everybody.
Thank you very much, Joe.
Amen.
Yeah, amen, Scott. Thanks.